Hello, friends. We're continuing our study of logarithmic functions by looking at them as the inverse of an exponential function. Okay, so what we learned last time, the general form of a logarithmic function, right? So f of x a log b of x, right, where a is the coefficient in front and b is the base. The base cannot be 1 because if that were the case, every exponent of 1 just creates a 1. So we would end up with many inputs for just the one output of 1. So we can't do that. And same thing, a can't be 0 because then no matter what we put in for x, we just keep getting 0 coming out. And that would be many inputs for one output, and that's not a function. So um, because exponentials and logarithms are inverses of each other, we would expect that the input-output patterns for exponentials would be switched for logarithms. So for example, in an exponential function, we have, if you look, the inputs are additive, right? Like in this example, we're adding 2 each time, but then the outputs are multiplicative, so times 2, times 2, times 2. So we would expect that those properties, right, to be switched for a logarithmic function, and that's what we have here, right? So just the inverse, right, the logarithmic version, the logarithmic inverse of the exponential function that we were just looking at, f of x, here g of x. So notice g of x, the input is sorry, the input is multiplicative over equal length intervals, right, additive intervals for the output. And so just from looking at that pattern, we can decide if these um, samples are additive or exponential or logarithmic or neither. Okay, and so this first one, if we look, this is additive, so it's like +1 every time here. And here we're dividing by 2 or multiplying by 1/2 as we go down. And so this one is going to be exponential. Okay, for B, the inputs look like they're being multiplied, right? So this is a difference of 20. So like times 3, times 3, times 3. Okay, so that's multiplicative, but the outputs are additive, 10, 20, 30, 40, etc. So this one is going to be logarithmic. C, C, it's it looks, well, what does it look like? It goes by 1 and then by 3. Really, it's multiplying. The outputs are changing multiplicatively, but so is the input as well. Right? Times 10, times 10, times 10. And so this is neither, because for exponential and logarithmic, either the input or the output is multiplicative, and then the other one is additive. Here, they're both multiplicative, so it's neither one. For D, okay, um, the the inputs, right? So what is this? Times 2, times 2, times 2, right? So this is multiplicative. Um, and the outputs are just, we're subtracting 3 every time. So it's additive in nature. So this would also be logarithmic. That's it. That's all we're worrying about for now, is identifying it as logarithmic or exponential based on the patterns that we see for the input and the output. Okay. Remember, when we did inverses, we said that if a function is an inverse of the other, then we could make the composite of the functions, take the composite, and we should get x as the output, right? Also, if the point x1, y1 is on the graph of f, then for the inverse, y1, x1 should be on the graph of the inverse. So let's take a look at some examples of this. If f of x is 3 to the x, so it's an exponential function, and g of x is log base 3 of x, logarithmic function, show that these are inverses of each other. So f of g of x, so this would be 3 to the power of, and then g of x, I plug in log base 3 of x. Okay, what does this mean? Well, for log base 3 of x, what I'm saying is, what is the what's the power of 3, right? That'll give me this output, right? Um, because I'm always asking, 3 to the what power will give me the thing that's in there, right? So 3 to what power will give me x, right? And then, but notice that 3 is to that power. So 3 to the power of 3 that would give me x is going to just give me x, right? So again, think of it this way. You could put in a particular number as an example for yourself, right? So you could say like 9, right? So log base 3 of 9 would be 2, right? But then if I take 3 to the second power, I get 9. And so rather, what ends up happening is then here, this is 3 to this thing. And what is this thing? Well, this is what I had over here, to the log base 3 of, and in this case it was 9, but it could be anything, is just going to give me x. So that I've shown that they're inverses of each other. And we could, the other way too, of course, log base 3 of 3 to the x. Okay, so I'm saying 3 to the what power would give me the same thing as 3 to the x. Well, the answer is just x, right? What power do I put onto 3 to get 3 to the x? Well, it's easy, it's just x. Okay. And so you're seeing a couple of, it's just properties of inverses, but also some simplifications that can happen. When we see something like this, like log base 3 of 3 to the x, then that simplifies to just plain x. Okay. And then same thing too with 3 to the log base 3 of x, then that just simplifies to x. And we're going to see that showing up in some properties that we study later on. Another consequence of the inverse nature of exponentials and logarithms is what we know about inverses of graphs. And so if we have a graph of an exponential function, in this case, 2 to the x, the way that we get the graph of the inverse is by reflecting over the line y equals x, right? This is the line y equals x. Okay. And so I'm going to get a couple of key points here. So here's a key point 1. So I reflect that over the line y equals x. And so it's going to go through here. This line, the exponential, is asymptotic here, right? So it looks, we could say like it kind of looks like it's going through -5. It's really not. So that means that the logarithmic function is going to be exponential this way, right? And then this is also going through the point here. The exponential is going through the point 1, 2. So that means that the logarithmic is going to go through the point 2, 1. Also, the exponential is going through the point 2, 4. And so this is also going to go through the logarithmic is going to go through the point 4, 2. And then I can continue this graph like that. So that's the reflection over the line y equals x using some key points and methods of creating the inverse graph. And I'm taking the inverse of the exponential function in order to get the graph of the logarithmic function. And example 4, the exponential function h of x equals a to the x contains the points 2, 3 and 6, 27. Find the average rate of change of y equals log base a of x over that interval, over the interval 3, 27. Okay, well, since log base a of x is the inverse of a to the x, then I just switch the points, right? So h to the -1, you could say, of x would have 3, 2 and 27, 6. And I'm looking for the average rate of change. So again, it's like the slope between those 2 points from 3 to 27. Well, that's what I have here, from 3 to 27. So I take those 2 points and I find the slope. Y2 minus y1 over x2 minus x1. So I end up with 3 over 24, which turns out to be 1/6. Sorry, 4 over 24. Arithmetic correctly here. 4 over 24, which is 1/6. Okay. And so again, all we did here was we were looking at the idea that the logarithmic function is the inverse of the exponential function. And then some different ways of looking at it, from tables, from points, from graphs, um, rewriting it, and then identifying from a table whether or not a function is exponential or logarithmic. So thanks for watching. Don't forget to like and subscribe.